Hello friends, welcome back to this series on Statistical Mechanics. In Lecture 2, we gave a short introduction to quantum mechanics and also calculated the partition function for the simple case of the ideal gas. 2 exercises related to these topics have been given in the lecture. Let's now go through their solutions. We shall also throw in some discussions about the wave packet of a particle and how it evolves in time according to quantum mechanics. This will help us identify the Hamiltonian that generates time evolution in quantum systems, which we didn't really get into in Lecture 2. Let's begin. The first exercise is about normalizing a Gaussian wave packet. This wave packet is built from the superposition of plane waves with a Gaussian momentum distribution. In this exercise, you were asked to find the constant n, such that the normalization condition is satisfied. To do this, we must first find the wave function psi tilde by calculating the integral in the blue box. We can simplify the form of the Gaussian function by changing variable this way. It is now straightforward to apply the standard identity for Gaussian integrals in the yellow box, which can be derived by completing the square in the exponential, making the appropriate substitutions for the parameters a and b. The integral in the blue box is easily solved. Now for the exponential term. Simplifying this factor in front. And we have the position space wave function psi tilde. Now we are ready to integrate over its absolute square. Notice that the plane wave is eliminated. We have assumed the factor n to be real. Once again, we can use the Gaussian identity to solve the integral in the blue box. This is won by the normalization condition. This gives us n. And we have the answer to our question. Let's simplify this. Thus we now have the normalized wave function in position space. As discussed in Lecture 2, this can be written as the bracket between the position state and the state psi p0. Let's express this in the earlier integral form. The first term under the integral is the plane wave, or the momentum wave function, which means the second term is the wave function of the state psi p0, but now in momentum space. This is so because we can view the whole integral as the insertion of the identity operator in momentum basis into the bracket that defines the position wave function. Now we can compare the position space wave function with its momentum counterpart. They are related by the integral relation below, which is basically just a Fourier transformation. Since the position space wave function is normalized, This means the state vector psi tilde itself is normalized, which naturally implies that the corresponding momentum space wave function is also normalized. Here we have verified the well-known fact that a Gaussian function turns into another Gaussian by Fourier transformation. Let's compare the spread of these two Gaussians. We can put the position space wave function into a form similar to its momentum counterpart, with delta x as a spread in position space, which is defined in the blue box. This equation relates the position spread of the particle to its momentum spread. Let's rewrite the constant factor in front and use the relation in the blue box. Now the similarities between the two Gaussians become even more apparent. The equation in the blue box is just a special case of the famous Heisenberg's uncertainty relation. In fact, it saturates the inequality. This means the Gaussian wave function describes a state of minimum uncertainties shared between position and momentum. Since we are talking about wave packets, let's see how they evolve in time. Classically, this is how light waves propagate. The angular frequency is related to the wave number by a linear dispersion relation, where c is the speed of light. If this is a wave function, we could derive this from how a quantum state evolves in time. We have discussed this in Lecture 2. If this wave packet describes how a particle is localized, then we could maybe relate the motion of the wave to the motion of the particle itself. And this will allow us to figure out exactly what the Hamiltonian operator should be. In Lecture 2, while we have defined this as a Hermitian operator that generates time evolution in a quantum system, we stop short of providing a prescription for this operator. This discussion will fill that gap. Note that the insight is this. If we view the wave packet as the wave function of a particle, and if this is observed at a low enough resolution in space, such that the wave function does not collapse into a smaller region, then this wave packet should seem to us to move like a classical particle, with the center of mass of the packet tracing out a definite trajectory, according to the familiar laws of classical mechanics. This is sometimes called taking the classical limit. You can find out more about this in Lecture 4 of my series in Quantum Mechanics. See the link in the description. Let's assume a general dispersion relation where omega is some function of k. Furthermore, assume that the distribution in wave number be very narrow and concentrates around a particular value k0. This means the spread delta k is very small. This suggests that the momentum of the particle is approximately h bar k0. If we now expand omega k around k equals k0, the higher order terms could then be neglected since these are only significant for large deviation from k0, but in this situation, gk will be small. So the wave function is mainly built out of the superposition of plane waves with k close to k0. This coefficient of the linear contribution, which is the derivative of omega with respect to k evaluated at k0, is called the group velocity of the wave packet. As we shall see, this group velocity corresponds to the average velocity of the wave packet. Let's split this plane wave into two parts, such that one of them is independent of k and can be brought out of the integral. We want to put all the k dependence as k minus k0, since the function gk is centered at this value. Notice that the term in the red box is the wave function at initial time t equals 0, with x minus vgt in the position argument. Except for this extra plane wave in front, but these phase factors will not matter when we calculate probability density. From this, we have an equation telling us how the probability density over position space changes with time. Basically, the wave packet is translated along the x-axis with velocity vg. This is why we call it the group velocity of the wave packet. More accurately, the width of the wave packet should spread out over time due to the initial uncertainty in its momentum. But due to our earlier assumption of this uncertainty being small, this effect is neglected. This group velocity can then be equated to the central momentum of the particle divided by the mass of the particle. The derivative of omega with respect to k can be written as the derivative of energy with respect to momentum, according to Planck's and de Broglie's equations. Thus, we have a differential equation relating the energy of the particle to its momentum. The solution is nothing but the non-relativistic kinetic energy of a particle traveling freely in space. If we identify the Hamiltonian as the operator that represents the energy of the system, H can then be constructed out of the momentum operator in exactly the same way. And it follows that the momentum states are also energy eigenstates for this particular example, with eigenvalues that match those in the red box, which correspond to the appropriate oscillation frequencies for the wave packet. To justify our assumption that the Hamiltonian that governs the time evolution of our quantum system is really its energy, we just need to equate the wave packet to the time-dependent wave function in position space, then make the time evolution due to h explicit. If we select the initial state appropriately, this is the obvious choice. We can reproduce the wave packet above. This prefactor is to cancel the normalization factor of the momentum wave function. Applying the Hamiltonian and the green box on the momentum state P, we have Now substitute in the yellow box. Here we change variable to k. And indeed, we could reproduce the time-dependent wave packet from quantum time evolution as long as the energy of the system is prescribed as its Hamiltonian. Although in this example, we are describing a particle moving freely in space, this rule can easily be generalized to the case with interactions. For example, we could include in the Hamiltonian the potential energy of the particle when the particle is moving through an external field. In other words, we simply identify the Hamiltonian of a system with its total energy. The second exercise has to do with a more general form of Gaussian integral. We encounter this while trying to calculate the partition function of a system with m quadratic degrees of freedom. The energy of the system consists of terms where different degrees of freedom couple with each other through the matrix A in a quadratic way. This matrix is symmetric and has positive eigenvalues. Our task is to evaluate this partition function and calculate the average energy of the system. The key is to notice that this integral can be put into a form of an ordinary Gaussian integral, by an appropriate change of variables. The entry point to this is based on the well-known fact about symmetric matrices like A. A can be written as a diagonal matrix multiplied by a matrix O on both of its indices. The diagonal entries of this matrix are just the eigenvalues of matrix A. O has the property that contracting two of them by an index gives a Kronecker delta that carries the remaining indices. Or to write this in a more familiar form of matrix multiplication, we have O times O transpose gives the identity matrix, which means O is an orthogonal matrix. We say that the matrix A is diagonalized by O. It is a well-known fact that all symmetric matrices can be diagonalized this way. One obvious fact that we have assumed up till now is that A and the other quantities are all real. This stems from the fact that the energy E is real, as well as the variables Q. Now we substitute this expression back into E. Now we transpose both of these O's such that these look like matrix multiplications, just to make them easier to read. These two terms quite naturally tell us what variables we should change to. The new variables are now all decoupled from each other. This is the form of a standard Gaussian. This result is entirely expected and is the reason why we diagonalize the original matrix A in the first place. The coefficients to Q bar square, the AKs, are the positive eigenvalues that we have mentioned before. And the reason why they must be positive is now clear. This is so that the Gaussian integral will converge. This is the same point made in lecture 2. Now we need to work out the integration element in terms of these new variables. That is, we need to calculate the Jacobian of the transformation. This result turns out to be trivial. The Jacobian matrix is the partial derivative of the new variables with respect to the O, and this is just equal to the matrix O transpose. Since O, and by implication O transpose, are both orthogonal matrices, this implies that the Jacobian, which is the determinant, must be equal to 1. This is easy to see by taking the determinant of the orthogonal condition. Thus the integration element is unchanged by the change of variables. When this expression of E is substituted back into the integral, it simply factors into m Gaussian integrals. Each of these can be solved by the standard identity. Since what we want is to calculate the average energy, we are only concerned about how log z is dependent on beta. While all the variables that are not dependent on beta are collected into the parameter tilde alpha, which we can ignore. Using the equation above, we can see that each quadratic degree of freedom carries the same energy on average, half kBt. This is the equipartition theorem. In this exercise, we have shown that this theorem applies even when the energy of the system takes a more general quadratic form. If you like this video, Consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.